Thank you all for coming. This is a study of ZMIC, which is an RR Lyrae star. I'd like to thank the Great Salt Lake Institute, the Utah NASA Space Grant Consortium, and my research mentors, Julia Kamenetsky and Michael Fitzgerald. So first, I'd like to start off by talking about what an RR Lyrae is. Put simply, an RR Lyrae is a variable star. There's several different types of variable stars. There are eclipsing binaries, which are actually two stars that circle each other. While binaries are common, eclipsing binaries are not because of how the light comes to Earth. And then there are also Cepheids and RR Lyrae. Cepheids tend to be studied a little bit more because we know more about their period luminosity relationship. But they both have the same principle where they vary in brightness. Cepheids are a little bigger and have a period of over a day, while RR Lyraes tend to be a little bit smaller and have a period of less than a day. Now, a variable stars oscillate. And what that means is their temperature, size, and brightness changes. As you can see at the GIF on the right, as one of these stars has an imbalance between outward pressure and inward gravity, it keeps changing, so it will oscillate. And as it compresses, it heats up, and the added pressure initiates a greater amount of fusion in the core. And when that happens, the star turns or has a blue shift, which increases the fusion pressure, expanding the star out where the brightness decreases, and it has a redshift, which means it's cooler. And then it starts to compress back in, and it continues this cycle. And RR Lyrae will do this less than one or more than once a day. Now, in order to know about RR Lyrae stars, we need to talk about their period and luminosity relationship. Because over time, these stars have a very distinct period that correlates with their luminosity. That is to say, if we record the brightness over time, take many, many different points, and then we put them all into a single phase so that we are measuring, instead of a time plot, we have it over a single phase, so one cycle where it goes from bright to dim to bright again. We get something that looks like this, where our brightest point, when the star is in the middle that you can see, it's bright, and then it gets much dimmer as the star expands outward, and then when it compresses back in, it spikes again in brightness. And the magnitude of this is actually on an inverse scale, so you'll notice how the numbers go from 12.5 up to 11.5. It's inverse actually because of the Greeks. When they looked at the night sky, they would measure the brightest star as a 1 and the dimmer stars as a 5, and we kind of just stuck with this scale. It's also a logarithmic scale, so 12.5 in magnitude and an 11.5. 11.5 is 2.5 times as bright as a 12.5. This is a very logarithmic scale. But once we compress all this data into a single period, we are able to calculate the period, which is the measurement between the peaks. When we calculate the period, we are able to calculate the luminosity given a theoretical relationship given by Catalan in a paper written in 2008. And from that, we are then able to measure the distance. However, it begs to ask why we want to study these stars in the first place. And the first and biggest reason is that an RR Lyrae can be a standard candle, which means that we can use that star to measure the distance to other stars. Galactically, there has been a lot of error in the measurement of stars, so we don't know exactly where things actually lie within our galaxy. And this is another method to try and make these measurements more accurate. The second reason is we can compare it to the Gaia survey. The Gaia survey, Gaia is a satellite in space, and it took many, many photographs of the night sky and measured the relative distances to all those stars from Earth. If we are able to compare these two and they are in agreement, then we can say with some certainty that the star lies within that range. Now, the process for doing this is quite simple. We observed the star and developed a period luminosity relationship, as you saw on a couple of slides ago. For me, this process took about 2 weeks in collecting data. And we compressed it all down onto a single phase, which I will show you in a minute. And from that phase, we were able to find the period, the distance between the peaks. And then from that, we were able to find the absolute magnitude. When I say absolute magnitude, there is a difference between apparent magnitude and absolute magnitude. Apparent magnitude is what you would get if you go outside at night and look up at the stars. It's what you observe. However, the apparent magnitude, what you observe, is not how bright the star actually is because of interference like the atmosphere and interstellar gas. It is not the same magnitude. Well, once we find the absolute magnitude, we can compare it to the apparent magnitude. What that comparison allows us to do is find the distance to the star once we compare the brightnesses. And when we do that, then we are able to compare it to the Gaia survey. And this is just a photograph of a robotic telescope that we used. We did not actually physically point a telescope. I used telescopes from South America and parts of Asia. And we were able to program them so that they would lock onto a star's position and track it for a couple minutes while we collected data. And this is the data that I was able to obtain. This is just the same phase repeated twice. It's just to make it easier to observe. And what we were able to determine from this is that the RR Lyrae star ZMIC has a period of about 0.6 days, which is what you would expect from an RR Lyrae star. And it is also a type 2 because it has a sharp increase in brightness. Some are more gradual over time. And what we were able to determine from this, when we compare it to Gaia, there are a few things. The first is that our Gaia result said that the star ZMIC is around 1,200 parsecs away from Earth. Now, to get an idea of how far that is, 1 parsec is about 3 light years, which is the distance to Alpha Centauri, which is the closest star to Earth. So this is very far out there. Additionally, when we are able, and it does have an error, and that error is around 100 parsecs when measured by Gaia. When we measured it ourselves, we had 4 different filters that we used because sometimes you get different results from different filters of light, and some are more accurate than others. But when we were able to use our results for our filters, we found that there was around 100 parsecs in overlap, which I know seems significant, but when you're talking about galaxies, that's not too bad. But the most significant part that we were able to determine is that Gaia overlapped with our measurements, which would lead us to suggest that the period luminosity relationship suggested by Catalan is accurate and can be used as a method for determining the distance to RR Lyrae stars as a standard candle. Should be noted that I did this project with a couple other people, and one of whom measured a different star, but using the same relationship, his measurements did not agree with Gaia. So there is more research that needs to be done in this area. Thank you. Do you have any questions?
I have one, if that's
Go for it.
I was wondering, about, so you were discussing the blue shift in terms of the stars from earlier in your presentation. I was wondering, and apologies if you sort of covered this, but how you determine that, like that difference in the frequency of it. Is it just the difference in the light that reaches the telescope? Is there some other way that they're able to measure that?
So we did not have to worry about redshifts too much because redshifts typically are more significant when you're looking at other galaxies, although they are very much still prevalent in our own galaxy. However, we were just measuring the magnitude of the brightness that reached the telescope, so we didn't have to worry about the frequency that much.
Okay. Awesome.
Josh, this is Bonnie. Can I ask, I think you explained this, but I want to make sure I understand what makes this useful as a standard candle. Is it because it agrees with Gaia? Is that like why it would be good as a standard candle? I love that term, by the way. That's my new favorite science word.
It's a cool one. Well,
Yeah.
standard candles, the idea behind them is it is a single star that you know the distance to. And when you have a couple of them, you're able to use them to determine distances to other points in the night sky, or other stars, if you will. And the difference between a standard candle is that you use different types of relations to figure out the distance to them. Like for an RR Lyrae, we used a period luminosity relationship to determine the distance to that star. It's not a direct measurement. And then we use that to find the distance. And Gaia, once you have a standard candle, you can use another method called parallax to find the distance to the closest stars. And so we want to get as accurate as possible the distance to a standard candle, because then it makes measurements to other stars more accurate as well. And you can get a more accurate view of the night sky.
That's an excellent answer. Thank you. Anyone else with questions?
I have one quick question. So is there any particular reason why you chose this star?
It had a cool name. No, there wasn't a whole lot of reason. We had to pick an RR Lyrae, and looking through all the stars, this star has been fairly well documented, but there hasn't been a whole lot of information on its period luminosity relationship.
Cool. All right, one more question. Preston has a question.
Yeah, a simple one. Over what distance range is this technique useful? Can it measure distances to other galaxies, or is this just within the Milky Way?
So this is largely just in the Milky Way. There are several different methods that you can use. The reason we want to get a standard candle is because it's useful with parallax, but parallax doesn't work over distances that go over to other galaxies, for example. But it is much more accurate than, say, measuring a redshift directly. If you were to measure a redshift of, say, Zemic, the star in here, it wouldn't be nearly as accurate.
Excellent.
Thank you.
So if you can